Welcome linear algebra fans, a video on 4 subsets. So in this video, we'll start by introducing a new null space called the left null space of a matrix. We'll see a strategy for computing column spaces that's a little bit unusual but insightful. We'll extend that strategy to what's called the extended echelon form, and then we'll be able to define these 4 subsets of a matrix in terms of that extended echelon form. Here's the definition. If A is an M by N matrix, the left null space of A is defined as the null space of A transpose. Okay, so this is something we know about, right? We know how to do a transpose and we know how to find a null space. So finding the left null space of a matrix is fairly straightforward. We start by computing A transpose, and then we just find the null space of the transpose. Okay, so here's an example. Let's go ahead and find the left null space of this matrix A. We see that A transpose has the following reduced row echelon form. We can identify that x4 is a free variable. We can identify that there are 3 pivots, right? So there should be n minus r equals 1 vector in the null space. Here's that 1 vector, minus 2, 3, minus 1, 1. So the left null space of A similarly is minus 2, 3, 1, minus 1. Span of the set of vectors containing that 1 vector. I'll point out that when A is 4 by 3, that the null space of that matrix A is a subset of C3, whereas the left null space of that matrix A is a subset of C4. So a little bit like the row space and column space from our last example. These things are hard to compare. As it turns out, however, they are again related, which is pretty cool. Okay, let's go ahead and think about column spaces, and here we'll think about computing a column space from a different perspective. So here is a really big matrix and a messy matrix. This is a matrix A. We know that by definition, an element B is in the column space of A if and only if the related linear system with coefficient matrix A and vector of constants B is consistent. Okay, so we know how to address this question of consistent also, right? We can take our matrix A, augment by the vector B, reduce, reduce, reduce to row echelon form. And in theory, we could do that for sort of an arbitrary vector B that just contains the elements B1, B2, B3, B4, B5, and B6. So Beezer in his book suggests that you follow along at home and work through this. And you could do that. And there's a lot of room for error here, but here's what you should get if you augment by an arbitrary vector B and reduce to row echelon form. You should get something that looks like this. Okay, so this again is a really messy matrix. We can see the reduced row echelon form of A here, and then we see this sort of mess vector of constants that we get from doing all those row operations on A. Okay, so as it turns out, of course, we know that B is in the column space if and only if the linear system is consistent. In order for the linear system to be consistent, we know that this element has to be 0 and this element also has to be 0, right? We have to have that row of zeros at the bottom in order for the system to be consistent. So that tells us that B is in the column space if and only if B is a solution of a certain homogeneous linear system. Okay, so here's what that homogeneous linear system is, right? I'm just picking off those two equations or those two expressions on the right-hand side, setting them equal to 0 and cooking up a homogeneous linear system based on those equations. Okay, so we can think of this as a homogeneous linear system with coefficient matrix L, right? So the coefficient matrix L you can find by just picking off the coefficients here of this homogeneous linear system and shoving them into a matrix. Okay, so that matrix, of course, is going to have 2 rows and 6 columns. Okay, so here's what you get for that matrix. We know that B is an element of the column space of A if and only if B is an element of the null space of this matrix L. Okay, and we can cook up an expression for the null space just by writing down two elements or elements that span that null space. Okay, we know that this homogeneous linear system has two pivot columns. It has four non-pivot columns, so it has four free variables. Here we fill in those four vectors, those n minus r vectors, with zeros and ones in the appropriate rows, so that b is the right value for those elements, and then we can fill in the rest just like we've done before. Okay, so before we would call this the vector form of the solution to the homogeneous linear system. We know that we can pick off these four vectors, throw them in a set, and that set is a linearly independent set that spans the null space. So we see then that the null space of L is the span of these four vectors, and similarly the column space of A is also the span of these four vectors. Now, as it turns out, this always works, and again, this leads us to the discussion of the extended reduced row echelon form. Okay, so extended echelon form is what you get when you augment a matrix by the identity with the same number of rows and reduce that new matrix to reduced row echelon form. What you end up with is a matrix B that's exactly the matrix A in its reduced row echelon form, and a matrix J that tracks what happens to the matrix I, the identity, by reducing A to reduced row echelon form. We can do what we've done before, which is to kind of put this in block form, and as it turns out, when you put this in block form, the matrix L that's the right of all of the rows of zeros from the reduced row echelon form of A ends up being exactly the matrix L that we just saw a moment ago. So I won't go through the proof of the theorem, but I'll ask you to reduce this to extended echelon form and identify those matrices B, J, C, K, and L from that reduced row echelon form, or rather from that extended echelon form. In any case, here is the main result of this section that relates that extended echelon form, here we call that extended echelon form N, to the different matrices in that extended echelon form. Okay, the first result is that J is a non-singular matrix, and B has a property that is equal to J times A. We see that AX equals Y if and only if BX equals JY. If C is in its reduced row echelon form, it'll have no zero rows in R pivot columns, and L in its reduced row echelon form has no zero rows in M minus R pivot columns. Okay, so as it turns out, those matrices C and L represent the column space and the left null space, the matrix A. Okay, so those are the four subsets. The four subsets of a matrix A are the null space of A, that's also the null space of that matrix C, the row space of A, which is also the row space of that matrix C, the column space of A, which is the null space of the matrix L, and the left null space of A, which is the row space of that matrix L. Okay, and again here the take-home message is that extended echelon form gives those four subsets. This should be not here, this should just be an arrow, right? Take A, augment by the identity matrix, reduce it, and the matrix C and matrix L from our reduced row echelon, extended echelon form give the four subsets. Okay, so I'll challenge you to identify those four subsets for this matrix A for which we have previously found the extended echelon form. Okay, so I have a lot of information here, folks, pretty technical. I encourage you to spend some time with the extended echelon form, identifying those column spaces and null spaces of the components of that block matrix we get. Hope you've enjoyed this video on four subsets. Have a great day, and we'll talk to you soon. Bye-bye.